Essentially, in the last couple of years, since Oumuamua, we've discovered these 7 objects within the solar system.
Why wouldn't you have a conundrum for an object that has never been detected before?
Yes.
A class of object that we've never seen.
Yes.
Why wouldn't it be filled with things that
don't make sense?
That don't make sense.
Maybe there are just these other objects in the solar system that are doing the same thing. It's just we had never noticed them before, because how do you detect comets? You see their cometary tails.
Hence, dark comet.
Yes.
I get it.
Yeah. This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. Got Chuck Nice with me. Chuck,
What's up, Neil?
all right, man. I hear you're working on a stand-up special.
Yes, we are trying to sell it right now. So if you're
It's all done.
it's done. If you're at Amazon or Netflix, hi.
Okay. Well, good luck with that.
Yeah, thanks.
Good luck with that. So you know what we're going to talk about today?
What's that?
Dark comets.
Ooh, sounds like a Marvel movie.
I'm Dark Comet.
Dark Comet.
Dark comets. I've seen the term, and I don't know how they all define it,
Okay,
because my specialty is like galaxies and cosmology and
Yeah.
like what's going on in the solar
That's
system.
too small for you.
No.
Comets. Oh dear, we can't be bothered with comets, can we?
Dark comet. We have one of the world's experts on this subject,
Yeah.
Daryl Seligman. Daryl, welcome to Star Talk.
Hey, thank you for having me.
Yeah.
So you are an assistant professor at Michigan State University.
Yeah, well, starting next year, I'll be an assistant professor. Right now, I'm an NSF fellow.
Oh, that's between your PhD and your first tenure track job.
Yes, exactly.
So he's brand new.
Wow, look at that. Just birthed by the National Science Foundation.
Just birthed.
Look at that.
So the National Science Foundation has what's called a postdoctoral fellowship, where once you get your PhD,
Okay.
it's money. You just do whatever the hell you want.
Ooh.
And it's like freedom that wouldn't otherwise be there if you immediately went right into academia. So Daryl, what was the title of your thesis, if you can remember it? Because I barely remember the title of my thesis, because there's a lot of words and a subtitle, but it's about comets.
Well, it was actually about interstellar objects.
Interstellar
yeah.
objects. Okay, well, let's start there. For the longest while, we presumed there was stuff flying between the stars,
That's right.
but nobody ever saw one, because occasionally you'd expect them to pay us a visit.
Or at least pass through.
Pass through, that's what I mean.
Yeah.
They just come in and go out, and we've been looking for centuries.
Yeah.
And your main topic of study is something that doesn't exist yet?
Oh, well, no, I was pretty lucky because when I was a third-year graduate student, I was doing just pure fluid dynamics for astrophysics. And then as a third-year graduate student, Oumuamua was discovered.
So just to be clear, so a fluid to an astrophysicist is a what?
A gas.
A gas,
That's right.
exactly, okay.
Right.
Yes.
So liquids and gases are both fluids to a physicist.
Right.
Right,
That's
okay.
right.
So then why does Oumuamua have anything to do with fluid dynamics?
Well, it doesn't have too much to do with fluid dynamics, to be honest, but it was such an exciting opportunity that we just kind of dropped everything else
pivoted.
we were. Yes,
Oh,
we
look at
dropped
that.
everything else we were doing, and we started working on that. So I don't know how closely you were following back in 2017, but it was one of the most exciting times for astronomy because basically this thing got discovered and it was also moving super fast.
Right.
So it was only observable for a couple of weeks from ground-based telescopes, and then upwards of 3 or 4 weeks.
Wouldn't you expect it to be moving fast if it's coming in from interstellar space?
Yes, you would expect it to be moving fast.
And
But
why would it be faster than anything else?
so because the planets are all moving in the same direction around the sun, Oumuamua comes in and it's coming from a totally different direction. And then it looks like it's moving really fast compared to our motion.
Because we're going in opposite directions
Yes.
to each other.
Yeah.
Okay, got it. So Oumuamua, we found this thing,
Yes.
called it Oumuamua, which sounds Hawaiian.
It
Yes,
does.
it is.
I think
Hawaiian.
was it discovered by a telescope in
Yes.
Hawaii?
So it was picked up by Pan-STARRS, which is a telescope in Hawaii that is funded by the Department of Defense, and they're looking for near-Earth objects.
Okay.
So small kilometer-scale objects that some of which, yes,
Kilometer scale.
small,
Yeah.
yes.
To knock you on your ass.
Yeah, exactly.
So some of those objects are potentially hazardous. So it's very important that we find them with ample time to do something if
they're going to hit us.
exactly.
Ample time to kiss your ass goodbye. You need enough time to get that out of the way. Well, so it seems to me, from what you say, Pan-STARRS had no expectation of finding interstellar objects, but it has the ability to do so regardless. Is that a fair statement?
Well, that is true, but I think they originally designed Pan-STARRS hoping to find interstellar objects because for the last couple of decades, I mean, we know the solar system has ejected a good amount of material in interstellar objects. So it's not much of a stretch to imagine that other planetary systems would also be ejecting material and we would see them. And the only difference is you just see a small body, but it comes across the night sky and looks hyperbolic. But the fact that we hadn't seen any, we were trying to put limits on the number of them in the galaxy based on not seeing any. But the hope was that Pan-STARRS would find one.
Right. So if you don't see any for a certain amount of time, you can say there can't be more than this number, otherwise we would have seen it statistically.
Yes, that's exactly
Now, you
right.
said it was hyperbolic. Tell me what you mean there. Because some people are hyperbolic.
Essentially, in the last couple of years, since Oumuamua, we've discovered these 7 objects within the solar system.
Why wouldn't you have a conundrum for an object that has never been detected before?
Yes.
A class of object that we've never seen.
Yes.
Why wouldn't it be filled with things that
don't make sense.
don't make sense?
Maybe there are just these other objects in the solar system that are doing the same thing. It's just we had never noticed them before because how do you detect comets? You see their cometary tails.
Hence, dark comet.
Yes.
I get it.
Yeah. This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. Got Chuck Nice with me. Chuck?
What's up, Neil?
All right, man. I hear you're working on a stand-up special.
Yes, we are trying to sell it right now. So if
So
you're
it's all done.
it's done. If you're at Amazon or Netflix, hi.
Okay. Well, good luck with that.
Yeah, thanks.
Good luck with that. So you know what we're going to talk about today?
What's that?
Dark comets.
Ooh, sounds like a Marvel movie.
I'm Dark Comet.
Dark Comet.
Dark comets. I've seen the term, and I don't know how they all define it,
Okay.
because my specialty is like galaxies and cosmology and
Yeah.
like what's going on in the solar
That's
system.
too small for you.
No.
Comets. Oh, yeah, we can't be bothered with comets, can we?
Dark comet. We have one of the world's experts on this subject,
Yeah.
Daryl Seligman. Daryl, welcome to Star Talk.
Hey, thank you for having me.
Yeah.
So you are an assistant professor at Michigan State University.
Yeah, well, starting next year, I'll be an assistant professor. Right now, I'm an NSF fellow.
Oh, that's between your PhD and your first tenure track job.
Yes, exactly.
So he's brand new.
Wow, look at that. Just birthed by the National Science Foundation. Look at that.
So the National Science Foundation has what's called a postdoctoral fellowship, where once you get your PhD,
Okay.
it's money. You just do whatever the hell you want.
Ooh.
And it's like freedom that wouldn't otherwise be there if you immediately went right into academia. So Daryl, what was the title of your thesis, if you can remember it? Because I barely remember the title of my thesis, because there's a lot of words and a subtitle, but it's about comets.
Well, it was actually about interstellar objects.
Interstellar
yeah.
objects. Okay, well, let's start there. For the longest while, we presumed there was stuff flying between the stars,
That's right.
but nobody ever saw one, because occasionally you'd expect them to pay us a visit.
Or at least pass through.
Pass through, that's what I mean.
Yeah.
They just come in and go out, and we've been looking for centuries.
Yeah.
And your main topic of study is something that doesn't exist yet?
Oh, well, no, I was pretty lucky because when I was a third-year graduate student, I was doing just pure fluid dynamics for astrophysics. And then as a third-year graduate student, Oumuamua was discovered.
So just to be clear, so a fluid to an astrophysicist is a what?
A gas.
A gas,
right.
exactly, okay.
Right.
Yes.
So liquids and gases are both fluids to a physicist.
Right.
Right,
That's
okay.
right.
So then why does Oumuamua have anything to do with fluid dynamics?
Well, it doesn't have too much to do with fluid dynamics, to be honest, but it was such an exciting opportunity that we just kind of dropped everything
You
else
pivoted.
we were. Yes,
Oh, look
we
at
dropped
that.
everything else we were doing and we started working on that. So I don't know how closely you were following back in 2017, but it was one of the most exciting times for astronomy because basically this thing got discovered and it was also moving super fast.
Right.
So it was only observable for a couple of weeks from ground-based telescopes, and then upwards of 3 or 4 weeks.
Wouldn't you expect it to be moving fast if it's coming in from interstellar space?
Yes, you would expect it to be moving fast.
And why would it be faster than anything else?
So because the planets are all moving in the same direction around the sun, Oumuamua comes in and it's coming from a totally different direction, and then it looks like it's moving really fast compared to our motion.
Because we're going in opposite directions to each other.
Yeah.
Okay. Got it. So Oumuamua, we found this thing.
Yes.
Called it Oumuamua, which sounds Hawaiian.
It
Yes,
does.
it is
I
Hawaiian.
think was it discovered by a telescope in Hawaii?
So it was picked up by Pan-STARRS, which is a telescope in Hawaii that is funded by the Department of Defense, and they're looking for near-Earth objects.
Okay.
So small kilometer-scale objects that some of which, yes,
kilometer scale.
small,
Yeah.
yes.
It'll knock you on your ass.
Yeah, exactly.
So some of those objects are potentially hazardous. So it's very important that we find them with ample time to do something if
If they're going to hit us,
exactly.
Ample time to kiss your ass goodbye. You need enough time to get that out of the way. Well, so it seems to me, from what you say, Pan-STARRS had no expectation of finding interstellar objects, but it has the ability to do so regardless. Is that a fair statement?
Well, that is true, but I think they originally designed Pan-STARRS hoping to find interstellar objects because for the last couple of decades, I mean, we know the solar system has ejected a good amount of material in interstellar objects. So it's not much of a stretch to imagine that other planetary systems would also be ejecting material, and we would see them. And the only difference is you just see a small body, but it comes across the night sky and looks hyperbolic. But the fact that we hadn't seen any, we were trying to put limits on the number of them in the galaxy based on not seeing any. But the hope was that Pan-STARRS would find one.
Right. So if you don't see any for a certain amount of time, you can say there can't be more than this number, otherwise we would have seen it statistically.
Yes, that's exactly
Now, you
right.
said it was hyperbolic. Tell me what you mean there. Because some people are hyperbolic. You know, and we,
A different sense of the word hyperbolic.
yes. No, so it's the Flavor Flav of comics. Just, we knew it was hyperbolic because it was like, yeah, boy.
So it came into the solar system and left, and it's never coming back because hyperbolic means that its orbit is not bound to the sun.
got it. So everybody else has an orbit that is bound to the sun.
That's right.
So it'd either be like a circle or an ellipse.
Wow.
Yes.
Right. Okay.
Exactly.
So these comets that we see every once in a while, like a Halley's, right? So that's bound to the sun. That's why we see them every once in a while because
Yes.
they're going around and coming back.
That's
Wait,
exactly
Halley's
right.
Comet is like 76 years. So you only seen that once.
Why you got to do that to my life, man?
You ain't living to 152.
Come on. Cut a brother a break.
You will not be 152 years old.
I know I have hypertension, but damn.
Just saying.
Yeah.
So hyperbolic. So that would be the best evidence that it was not a member of the solar system, because comets are coming in from out far away all the time.
That's right.
So why isn't it just an asteroid? Why do you know it's a comet?
So there is kind of a continuum between comets and asteroids.
So now we get into word issues. You know,
That's right.
Word definitions.
Uh-oh.
Yeah.
So the things that formed at large distances from the sun, they have ice in them.
Which hasn't evaporated away
Exactly.
over the years, eons. Yeah.
Exactly. So when a comet gets close to the sun, the ice will heat up and sublimate, producing a dust tail. And that produces a bright, beautiful cometary tail.
You can't say evaporate.
Yeah, I can't.
Oh, right, it
Use the real word.
sublimates.
You
Yes.
got to use the real word.
Well, of course, yes.
You know, to regular folk, it's evaporating.
Yeah, exactly. But no.
Sublimates.
Yes.
Remind us what sublimate means.
So that is when the ice not just in a comet, but when ice transitions straight to the gas form.
Straight away without melting in between.
That's right.
Yeah, so what they call dry ice,
Oh, okay.
that just smokes away.
That right.
You've never seen liquid dry ice, have you?
No, you haven't.
Right.
It goes right to the. And now, ladies and gentlemen, coming to the stage. It goes straight from the ice
To the smoke.
To the smoke.
Yeah. In fact, if you have an ice tray in your freezer,
Okay,
you go
I
away
do.
on a long vacation and come back, the ice cubes are littler.
Yeah.
Have you ever checked this out?
I have seen that.
Yeah.
Yeah, you see them, they shrink up
They
inside
shrink
the
up.
actual tray.
Yeah, they're actually sublimating. Yeah, okay. So keep going. I interrupted you. We're distinguishing between
Comets
on
and
the
asteroids.
continuum of asteroids and comets. Go.
Right. we expected that the interstellar objects that get ejected from other planetary systems, that they most likely would have formed at large distances and then had a lot of ice in them. So we'd expect them to be comets.
Is that because if they form at a large distance, they're not strongly held by the gravity of their host star?
Yeah,
So they can be knocked off?
that's exactly right.
Okay.
And if they form at far distances, then they haven't been close enough to their host stars for the
lose the ice.
Yeah, so you get a double
That's right.
force going there.
So may I ask if they are forming at such large distances from their host star, what happens to get them to be kicked out so that they're now slingshotted out into, hey, I'm on my
Right.
way.
Yeah, no, that's a great question. So, and it's a good question because we also don't know the answer. But,
Stop asking our guests questions he can't answer, Chuck.
but the most likely thing is you basically have something like a deep space maneuver for a spacecraft where you slingshot off of a planet, but you have that with something as big as Jupiter.
I mean, their version of a Jupiter.
Right.
Yeah, their version of a Jupiter. So something with Jupiter's mass at around 5 astronomical units. Then if a small body gets close to that planet, it could get slingshot out.
So Jupiter is like a proxy sun or a Jupiter type. It acts like it would be the sun.
Well, it messes with the
it
messes with the orbits of
Right.
things that
yeah.
go by.
It's more like when you get close to Jupiter, you start feeling its gravitational influence much more than the sun, and then that will change your orbit.
Gotcha.
Yeah.
Okay.
Yeah.
Now I get it.
Yeah.
I get it.
Jupiter intervenes.
That's right.
So, but also, presumably, given enough time, this other star system may get tugged on by other stars that happen
Yes.
to wander too close.
Yes, that's exactly right.
Yeah.
That it also can happen.
Okay. So, again, why are you thinking this was a comet instead of an
Right.
asteroid?
So Oumuamua, in every way we expected, acted the exact opposite. So the biggest thing was it had no cometary tail whatsoever.
So then why call it a comet at all?
Well, then it was initially called a comet because they made a mistake actually at the Minor Planet Center. Then they changed it to say that it was an asteroid because it looked inactive, which means that it doesn't look like a comet because it doesn't look like it has a tail.
Doesn't reveal fluff.
That's exactly
okay.
right. But then we realized as we were trying to get follow-up observations with the Hubble Space Telescope and the Spitzer Space Telescope that the object had a non-gravitational acceleration.
So Spitzer specializes in infrared, if I remember
Yes,
correctly.
that's exactly
okay,
right.
Good.
Yeah.
So you want to combine different tools out of
Yes.
the toolkit of the observational astronomer to see it in as many ways as you can.
Yeah.
Okay.
And Spitzer is really great. Like looking in the infrared is really great for comet science for some of the same reasons you use it for things like exoplanets, but because you can see typical cometary gases like CO2 and CO that you wouldn't be able to see from the ground.
So Spitzer, named for Lyman Spitzer.
Oh, okay.
He's a former chair of the astrophysics group at Princeton University.
Ah.
And I have one of his books on my show.
I was going to say, you sound like you know him. The way.
So I keep interrupting you.
No, that's
Yeah,
okay.
keep going. Go.
Essentially, it had this non-gravitational acceleration, but no apparent dust coma. And then an important point is that these non-gravitational accelerations, we see them on. So first of all, what that means is that the object, you look over time at its position in the sky, and then you figure out its orbit, and then you realize that its orbit could not be explained just from the sun's gravitational influence. So there must be an additional force acting on it. And we measure that.
That's what you mean by non-gravitational.
That's what I mean by non-gravitational. So we measure that in comets all of the time. So there are many comets with non-grav, and I might even slip up and just call them non-gravs, but these non-gravs have been measured, and that's happening because as that ice sublimates, it produces like a rocket type recoil effect.
Oh, okay.
So every little bitty jetty thing
Yes.
that comes off, that's a force operating on its
That's right.
trajectory.
Yes, that's exactly right.
So that alone is not unusual or uncommon.
That alone is not uncommon. That's
but
correct.
it didn't have any fuzz.
That's right. Exactly.
And you want there to be fuzz if you're going to be non-gravitational.
That's right.
So
because
now you're in a conundrum.
Yes. And there is another kind of important point, which is that you will also see asteroids accelerating non-gravitationally. It's just that their non-gravitational accelerations, for example, they can be caused by solar pressure, radiation pressure. They're much, much weaker. So Oumuamua's non-gravitational acceleration, the weird thing is not that it had one, it's that it had one with no dust coma, but it was much stronger than those that could be operating on an asteroid.
So, because I think asteroids, many of them are very dark. so that they would absorb sunlight.
Yes.
And that if you're absorbing momentum of photons.
So it's like a solar sail at that point.
Oh yeah, well the solar sail
Just
would
moving
reflect light.
extremely slowly.
Right. Yeah, so I'm saying
but in
super-
either case,
Yeah.
the light pressure
It's
is
the pressure of the
acting on the
Yeah,
that's
system.
great.
Okay, so it's a nice conundrum. And by the way, 'cause I'm a big reader of the history of science,
Yeah.
why wouldn't you have a conundrum for an object that has never been detected before?
Yes.
A class of object that we've never seen.
Yes.
Why wouldn't it be filled with things that
don't make sense.
don't make sense?
Right.
Well, it basically made me think like I am really grateful for Oumuamua because I feel like Oumuamua, if you look back for the last couple of decades, it was the most intensely studied small body over a very short period of time. So there were something like 700 and something observations over the span of a couple weeks, just of this one object.
That's evidence of how unusual it was.
Right. But because of that, and because we then had to point Spitzer and Hubble at it, we then had to get the trajectory really, really accurate. And then we noticed this non-gravitational acceleration. So it made me think maybe there are just these other objects in the solar system that are doing the same thing. It's just we had never noticed them before because how do you detect comets? You see their cometary tails.
Right.
You don't see the non-gravitational accelerations,
Hence,
which are actually...
dark comet.
Yes.
I get it.
There we go.
Okay. Is there a consensus? Because we're now 8 years into it, right?
Right.
So you should know something by now.
So I would say that, well, I would like to say that me and Jenny Bergner's recent theory about Oumuamua is the consensus, but unfortunately there are a lot of theories.
Einstein had a theory. You had an hypothesis.
We had a
Okay?
hypothesis,
So
yes.
say that again.
Neil gets very touchy about his theories and hypotheses. Okay.
Fair enough. I respect
You
that.
in my office here at the Hayden Planetarium Museum of Natural History. You're going to say it right.
Yeah,
Okay.
you're in very good company, by the way, of people who was like, no, you have a hypothesis.
Okay, go ahead.
So Jenny Bergner and I have this recent
This
hypothesis.
is a collaborator.
A collaborator of mine who's a professor at Berkeley. Essentially, Oumuamua was similar to a dark comet, that it was, the acceleration was driven by the outgassing of volatile-like, ice-like material, but it just had very little dust coma. And that's why we didn't see the dust coma for whatever
Okay,
reason.
so that would explain it.
Yes, that would
A
explain
little
it.
bit after the fact, it'd be better if you had predicted that such a thing would exist.
Right.
But now you're just forced to sort of kludge an answer, which
Yeah.
sounds plausible.
Yeah.
But have others followed behind it?
So there's a lot of argument about what the type of volatile that was driving it.
Explain to people what volatile is, because any normal person thinks if something volatile, it means it'll burst into
Explode.
flames. Right. So geologists have a whole separate usage of the term. So catch us
Right.
up on that.
Yeah, it just is about what type of ice could be driving the acceleration. So
No, just a volatile thing.
a volatile thing
what?
is something that has ice in it.
Oh, only that? I thought
Yeah.
it
When I say volatiles, I just mean ices, basically, because when you put them in space, they will sublimate.
Okay, so I thought anything that can turn to gas is volatile. Is that not true?
Well, that is technically
Isn't
true,
water
but
in space volatile?
yes. But so water in its ice phase is what I mean by volatiles.
Okay, and you wouldn't find a swimming pool of liquid water out there anyway. Right. Got it. Okay.
Yeah.
So in practice,
It all starts as ice.
it's ice.
Right.
It's ice that can sublimate.
Yes.
These are your volatiles.
Yeah.
Ice of any kind.
Yes.
Not just water ice, but like
Yeah.
ammonia ice, I guess.
Yes.
Maybe some more CO2 ice.
CO2,
dry
CO,
ice, right?
Water ice.
nitrogen.
Nitrogen ice. Okay.
Yeah, so they have that on Pluto. So there is nitrogen ice on Pluto. So to back it up, essentially in the solar system comets, the primary driver of activity, the main thing you see is water ice. And then you also see CO2 and CO, which is carbon dioxide and carbon monoxide. So those are the typical ones. But with the Oumuamua Spitzer, the reason they looked at that is you would identify CO2 and CO.
Because those have spectral signatures
Yes.
in the infrared, with
That's
Spitzer
right.
especially capable of detecting
Seeing it.
in ways that Hubble would not be able to.
That's right. So another issue is that without getting too much into the details, essentially water could not be providing the acceleration because there was not enough energy from the sun.
To sublimate the water.
Yeah, that's right. Sublimate enough water to provide enough push to
Push.
get the acceleration.
Cool.
But a much better accelerant is hydrogen. So our hypothesis, not theory.
He thought about it too. He was like, so Howard, I'm going to say it because I'm here.
Okay.
The hypothesis is that there was water ice in Oumuamua, but then as it travels through the interstellar medium, it's exposed to these very high energy particles called cosmic rays, and that will break down some water and trap hydrogen in there. And then as the ice heats up as Oumuamua comes through the solar system, it will just gently release this trapped hydrogen.
Which has a greater impulse to accelerate the object than just evaporating water would.
That's right. So it's both the fact that hydrogen is a lot lighter than water, but also it takes much less energy to sublimate hydrogen than water.
Wow. Okay.
Wow.
So, all right, but you said there's nearly 1,000 papers on this object.
That's right.
And you're saying, but you and your colleague have this hypothesis.
Right.
Are you lone wolves out there?
No. So essentially, it comes down to can a hypothesis explain all of these mysterious properties? Another thing is you could have the acceleration driven by radiation pressure. It's just for that to work, it would have to be ultra thin or ultra low density. So Amaya Moore Martin at Space Telescope has this idea that it was an ultra low density fractal aggregate, which basically means it's a very large snowflake.
So it's large, but with very low
Right.
density.
Yeah.
That's right.
Right. So there's a lot of.
So you can push it.
That's right.
You can push it. Yeah.
Yeah.
That's right. So the solar photons, which very subtly push asteroids, could suddenly push
Push
this
this a
thing.
lot,
Yeah.
like right.
So because
like,
it's not
a lot harder.
Because it's not doesn't have a orbital companion, there's no way you can know the mass of this thing. You have to make assumptions about
Yes.
it.
So yes, that's totally right. Yes. That is a detail that I intentionally swept under the rug, but yes.
No, this rug here is clean. All right. So is that the betting person's explanation? The way to test this was, is there another one of these objects?
Right.
And I seem to remember there was.
Yeah, so there was another one, another interstellar object, but this was 2I Borisov. So that was detected in 2019. And that was very clearly a comet. So that had a big dust tail.
Okay.
But the exciting thing is that the Vera Rubin Observatory in LSST, which I'll probably refer to it as, is coming online just next year.
Vera Rubin, another astrophysicist, died a few years back. She discovered dark matter in galaxies back in the 70s. So we named a whole observatory after her. And this is an observatory that, unlike any other, in what important way?
Right. So it is coming online right now at the beginning of next year.
That would be 2025.
2025, right.
What's the observatory going to do?
So it's going to observe the entire southern hemisphere almost every night. So it'll be like pan-stars now, which is in the northern hemisphere, but it'll look almost every night to see anything moving in the sky, but it goes almost 5 orders of magnitude more sensitive than pan-stars.
So 5 powers of 10.
Yeah. So we'll be finding many more moving objects in the solar system, and we should be finding many more interstellar objects.
I think
like
people
Oumuamua.
don't appreciate that if you just go to a telescope and get images and bring them home, you don't know if anything is moving on that image.
Right.
You know,
You got to get it over a period of
they're
time.
basically snapshots.
Right.
You need exactly those kind of data
Right.
to see if something goes bump in the night.
That's right.
So the Rubin telescope should blow open the whole field.
Yes. Absolutely.
Gotcha.
Wow. That's pretty cool.
So it's pretty exciting.
yeah, it
astronomy
is
right
yeah.
now.
And
All
so,
right.
okay.
Are there any other explanations for this?
Aliens. Come on, guys. That's just, why are we trying to act like we're not going to talk about the elephant in the room?
That's the easiest explanation.
That's what it's got to be, right?
Like ever, or ancient astronauts or something.
Right.
Yeah, whatever.
Exactly.
So I feel a little jealous because if Oumuamua got kicked out of some other solar system, star system, and we're a star system, red-blooded star system, we ought to have some Oumuamuas of our own.
I've been kicked out of better star systems than this.
Yeah.
Essentially, in the last couple of years, since Oumuamua, we've discovered these 7 objects within the solar system, which are near-Earth objects, actually, which is what Oumuamua was initially.
They thought it was a Neo?
Thought it was a Neo. That's right. You're picking up on the abbreviation also. So they thought it was a near-Earth object. So these are near-Earth objects which are bound to the solar system, unlike Oumuamua.
So they have elliptical orbits, not
Yes.
hyperbolic orbits.
That's correct. We discovered significant non-gravitational accelerations on all 7 of these objects, which are also inactive, which means that they don't have comet-like tails.
Oh, okay. So therefore you can't credit the normal comet non-gravitational outgassing.
That's right. But the accelerations we found on these dark comets, dark comets is just a name I made up. I think people like it, but
How could you not?
So these objects, essentially their non-gravitational accelerations are too strong to be explained by similar to Oumuamua, the accelerations you see on other asteroids. So we have the hypothesis.
That's awesome. That's awesome.
We have the hypothesis that these objects are like comets and that they have icy material in them, even though they are close to the sun and have been there for a long time. But they're, for whatever reason, not producing a large dust coma.
Could you have a layer of something other than ice that encases ice within it?
Ooh.
Yeah.
So that prevents a full up exposure to sun's energy?
Yeah, absolutely. And so that was actually an idea. That was an idea that I wrote a paper on that could have, for Oumuamua, like the interstellar medium, the cosmic rays basically could have produced an insulating shell around it that could have prevented outgassing. But that was before we knew that the non-gravitational acceleration was there.
Right. So just to repeat what I think you said, you have an object that's icy, has volatile ices, but cosmic rays basically turn the outermost layer of that ice into an insulating crust.
Yeah,
Right.
that's right.
Because the water molecule gets broken,
Yes.
and now it's no longer frozen water, it's just hydrogen and
Yeah, that's
oxygen.
right.
What happens to the oxygen?
Essentially, well, it depends where it is. Like in the idea that Jenny Bergner and I had, hydrogen and oxygen would be entrapped within the ice.
But separately from each other.
Yes, separately from each other. But this is more like you can create a kind of tar-like material on the. It's kind of like asphalt almost. But that's not what
carbon for
happened.
that?
So then what?
Yes.
Oh.
So,
So it
where
would-
do you get your carbon?
Oh, it would have been there originally.
Okay, well, and you get that in the CO2 or the CO. And
Yeah.
Carbon's not rare in the universe. This is cool. So,
But then how's it re-released then? Because
So
you insulated it, but then
the one thing is I was going to say though is that certainly is not what happened to Oumuamua, because I wrote that it took it was discovered in October and then it was May when the acceleration was published. So I wrote a paper before the acceleration was published that explained it like that, and I was certainly wrong about that. It's just that what I was saying was that
how many branches
But
of
you love
life
it. You
does
gotta
someone
love it.
say I was wrong?
yeah, well, listen, that's what makes science so great. It's
Right.
like we're right today, we're not tomorrow. We're right tomorrow about what we weren't today.
What'd you just say? It sounded good. Yeah. No, but just to be clear, we don't always say we're wrong about things that have been objectively shown to be true.
Right.
When I say, oh, E equals actually equals MC cubed, we didn't, who knew? No,
Right, no.
E equals MC squared, we're good there.
Right.
And so if you are in mid-hypothesis and it's being tested,
Right.
that can come and go. And if you're first out of the box with an idea,
Right.
that's highly susceptible to later
Yeah.
data that shows up.
But nothing better than you yourself
Correct.
making that adjustment or
Yes.
correction.
Yeah, that's right.
Than somebody else coming along and going, yeah, guess what, man? You're a dumbass. 'Cause this is the way it works.
It's an
Like,
official science
yeah,
term.
that's super cool, man.
well, I guess one thing is that these non-gravitational accelerations, like you were asking, why hadn't we seen them before in the solar system? So they're very difficult to detect. And so with the dark comets, most of them have been known about. There's one that I've been known about for more than 20 years. It's just people have been monitoring it for 20 plus years, trying to measure the position, and we finally noticed. So Davide Farnokia at NASA, JPL, basically has to figure out the trajectories of all the bodies in the solar system and include it in the fits for those non-gravitational accelerations. So there's kind of people all over the world who are monitoring objects that we know of and seeing if any of them could be potentially hazardous.
So you use the term "to fit" for it. What you mean, I think, is if it's pure gravitational, there's a formula where you can forever predict the future trajectory. But if you're not fitting the future trajectory, you have to fit it some other way, mathematically.
Right.
And so you add these other terms
That's right.
that you think you understand.
Yeah, and you also, he does it numerically just with a supercomputer, but you basically try all different types of accelerations. And
Do it numerically means you can't do it analytically.
Right.
Every step has to have a computation
Yeah.
that gives you a position in the trajectory.
That's hard.
Whereas if it's analytic, you can just run the formula and
Right.
it'll get you the whole way. Yeah, they're both effective, but one of them admits that we don't fully know the physics of what's going on, so we have to fit the model.
Yeah.
Fit a model to it.
Yeah.
So with the hydrogen and oxygen and comets and all of this, does this affect anybody's sense of where the water on Earth came from?
Right. Yeah. So this is also kind of based on this student who's been working with me, who's just started this last year.
You just got out of graduate school, and you got students already?
Good for you, man. I love it.
Man.
So that's Astor Taylor, who had a paper published that discussed the possibility that the water, that dark comets could have brought water to the Earth. So,
More so than other comets?
All right.
well, so people used to think that comets delivered water to the Earth, and we still don't know where the Earth's oceans came from. And part of the reason that we're now not sure if comets delivered the water is because we have spacecraft measurements of water in comets, like the Rosetta mission went to 67P, and some of the isotopes, which is some of the things about the water in that comet, did not match that we've measured in the Earth's oceans.
This would be deuterium. I
Yes,
guess, right?
yes. So that's
Yeah.
one of them. So the deuterium to hydrogen ratio.
Yeah, so hydrogen is just one proton in the nucleus. And the protons define what we label the element to be. So now you throw in a neutron.
Okay.
It's still hydrogen, but now it's like a little heavier.
Right. So you can't just, it's got to be hydrogen, something else.
Something you got to
You
do
need
something
with the name.
Right, and so we
'Cause
call it
can't-
deuterium.
Right.
How stable is deuterium?
Well, it's not that it's stable. It's just the important thing is that the amount of deuterium compared to hydrogen isn't going to change from processing. And it depends very critically at the temperature of
It won't
formation.
change chemically.
Right.
So if the comet doesn't match that in the oceans, you can't credit the comet
Right.
for delivering
That's
the water.
correct. So we don't know for sure, and Astor was very careful to say this in the press releases and news articles about their paper, but we can't say for sure that dark comets could have contributed water to the Earth. But they are entirely new population of small bodies that are
new
in
source.
a new source, potential source. They're in the vicinity of the Earth, and they potentially have volatiles. So we would need follow-up observations to figure out if they match up. But the Hayabusa 2 mission, the JAXA Space Agency mission,
JAXA, Japanese Exploration Agency? Something
yeah,
like
it's
that.
basically Japanese
NASA.
NASA. But their Hayabusa
Japanese
2
NASA.
mission,
What's JAXA?
it just
Not NASA, but JAXA.
I'm sorry, that just sounds very racist.
NASA came first, dude.
This is true.
America.
Okay. Listen, I don't have a problem with it. But go
so
ahead.
their Hayabusa 2 mission, in the extended mission, it just so happens is going to a dark comet.
Cool.
So in 2031, we're going to have
That'll blow it open.
Yeah.
it might, well, it's at least going to rendezvous with it, but we'll have enough sensitivity to measure things like outgassing or dust if it's there. So at the very least, the worst case scenario, we're going to have an answer to all of this in 2031.
Now, literally, comets.
Coming up on Star Talk, we've got a Cosmic Queries edition all about exoplanets. I've got with me one of the world's experts on that subject, Anjali Tripathi. Welcome to Star Talk. We're going to find out where she came from, where she's been, and where she's going in this world of not only exoplanets, but also as a citizen scientist serving 2 presidents. Coming up on Star Talk. This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. Today is another Cosmic Queries, ever popular format that is, on the subject of exoplanets. Chuck,
Yeah.
my co-host, how you feeling, Chuck?
I'm feeling great, man.
Feeling good about the exoplanet?
Exoplanets are always fodder for great thought because now we know that there are millions and millions of them. They're everywhere.
I don't know if the catalog has quite hit that yet.
We went from 4. They were like, maybe there's 4.
So I know a little bit about exoplanets, but if we're going to really go in with the Cosmic Queries, we're bringing the big guns.
Yeah.
Okay. So we combed the landscape and we found Anjali Tripathi. Anjali, welcome to Star Talk.
Thank you so much. So excited to be here.
Excellent. Excellent. You in your professional life, not only did original work on exoplanets, you also found yourself, either on purpose or otherwise, at the intersection between science and society.
Absolutely.
So I want to get to that in just a minute. Right now, you're a research associate at NASA's JPL,
Lovely.
which Chuck stands for what?
I believe Judy Paulson lingerie.
That's right.
Judy Paulson's lingerie. It's all the rage. No. of
That's
course.
usually classified. Why'd you let that one
That
out?
was classified
That-
information.
Yeah. Now the awesome Jet Propulsion Labs.
The Jet Propulsion Labs in Pasadena, California. Yes. And it's not only a branch of NASA, they collaborate and are basically on the campus of Caltech, right?
Yeah.
I am a Caltech employee.
Right,
yeah.
right. So who signs your checks? Is it Caltech?
It is
Caltech.
Caltech.
Wow.
Okay, there it is. But you
Okay.
still have NASA overlords.
I do.
I'm pretty sure you do. You know who we had on Star Talk just when she just started
Right.
was the director of JPL, Lori Leshin. She and I served on a commission to study the future of NASA.
Wow.
We were both appointed by President George W. Bush.
Nice.
And she went on to great things. And
And you,
You
Not
got
so
stuck with
much.
me. I'm so sorry. I'm so sorry.
what a shame. Oh,
but you could take the Lori Leshin episode out of our archives. That was fun.
right.
I wanted to get to her before NASA got to her, because NASA they want to over control the interviews, but she and I go way back.
Right.
So there was an interval where let's just rock and roll this. all right?
Exactly.
Just say what you think what you feel.
Yeah.
Put
Well,
up-
you're not going to be able to do that with Anjali because NASA is still controlling her. Sorry.
I got the NASA handcuffs
Yeah,
on. It's
Okay,
okay.
no, we'll figure something out here. So, at JPL, what are your primary concerns?
I like thinking about what can we see from space, right? So what can you see when you look up about exoplanets and other worlds, and also looking down here on Earth and how we can improve life here on it.
People, when they think of space exploration, they don't always think that from space you can see Earth
Right.
as a planet
Exactly.
and monitor what's going on and how we doing. So this seems to be a really important feature of what NASA can deliver the public.
Yeah.
It's something folks always get wrong. You ask them, what's our most studied planet at NASA? And they go, Mars. And you go, wrong. And you think, it's Earth. And nobody realizes that.
Yeah, exactly.
So you still have roots back where you got your PhD?
I do. Yeah, I'm a research associate at the Harvard Smithsonian Center for Astrophysics.
Okay, all right. So tell me, before we get back into exoplanets, because that's where we got all the questions are based on those.
Yes, they are.
The science and society part of your life, how did that begin?
So being a Valley girl, we had an earthquake in the 90s and I had to move out of my house for a year. And the people who come on TV, for those of you who've had the pleasure of earthquakes, it's a seismologist who comes and tells you what's going to happen. And I thought, scientists can come and tell you what's going to happen next and
Right.
sort of save things. I want to do that. And then I learned that seismology and geophysics and physics are important, but they don't save the world in the same way. And so thinking about how you can find connections between science and serving
You know why they
people.
don't save the world? Because they only bring the geologists on
After the earthquake.
After the
Exactly.
earthquake.
Exactly.
Not just before the earthquake, after the
It-
earthquake.
It's true.
Okay,
Yeah.
they ain't saving nobody.
It's a
okay?
doggone shame because, when do we really need them? We just got some readings in. That's when we need them.
Whereas with the astronomers, we're like, that eclipse, get ready. It's coming in 6 months.
Okay, so
Right.
total
Before.
predictive powers.
Yeah.
All right, so now what? So the urge doesn't make the reality. So what happened?
I mean, I was lucky enough. I went and served in 2 administrations. President Obama brought me in as a White
Oh,
House
she
fellow.
was lucky.
Wow.
That was just luck.
I was going to say,
That was just luck.
yeah.
I mean, I don't like to talk about the bribes.
I
though.
served in 2 administrations. That's funny. I used to serve at Wendy's. I was Wendy's manager, and I served for
two tours of duty.
For 2 tours of duty.
Wait, so who was
Thank you for your service.
who was your first president?
Well, I mean, I was born a while ago. Where lady doesn't reveal her age, but of the 2 administrations,
We're going to
President-
triangulate on that if you give us enough information.
President Obama.
President Obama.
Oh,
okay.
okay.
And so, in what capacity were you serving in the
So
White House?
I came in serving the U.S. Department of Agriculture, thinking about climate change. It doesn't matter why your soil is dry. You got to
Right.
get things to grow.
That's right.
Is there a relationship between the Department of Agriculture and the Environmental Protection Agency?
I mean, so I was working on food waste, right, which is something that
Big
both
deal.
care about, right?
Big deal.
Because,
Yeah.
I mean, your apple that you don't eat
Right.
turns into methane, which is
Methane.
greenhouse gas,
Yes,
right?
without a doubt.
So
All right. So, but you didn't just. So, how does the Obama administration connect you to agriculture? What is that pathway?
where else would you put an astrophysicist in government?
Wait, what was your title?
I was a White House fellow.
Oh, you didn't say that. Oh, okay.
Right.
A White House fellow. And so you have these science fellows at the White House.
So the White House fellows are actually, I was the only scientist.
Oh, I
Right.
didn't know that.
Yeah,
Okay.
so it's a group there were 16 in my class, right? So one of them is now a congresswoman. We've got all kinds of folks, a lot from the military and business and law. So the idea is you go and you serve a cabinet secretary as a senior advisor.
Because the cabinet reports to the president. So
Right.
this is still a
Correct.
White House thing.
Exactly.
So the Secretary of Agriculture then became.
Yeah,
Exactly,
okay,
right.
Who reports to the president, and you were working with them?
I'm intrigued by the fact that you get a PhD studying exoplanets. So you're thinking about planets, looking at them from afar,
Right.
and then Earth and agriculture becomes Earth that you're thinking about from afar. So what kind of NASA or astronomical insights can you offer the Department of Agriculture?
Well, I mean, I want it to be more down to earth, let's be honest, right? And the idea is just that, you can see so much more from satellites than you can with a guy.
Walking around with a mule.
Right.
Hey, they offered to send me to estimator school where they said you're going to walk a certain number of paces in a cornfield, pick the second ear of corn you see, and count the diameter and across. And that's how we estimate the crop yields in America. We still, to this day, don't use satellite technology for the government predictions on crop yields.
What? Was this Green Acres?
That
What?
was crazy. That's crazy.
You got Arnold the pig
Exactly.
predicting the weather? Like
Hey.
what?
Hey man, so how big is your corn? like that's crazy.
It's quantitative. You count,
Yeah.
But I mean, it's one of those things that it's really useful for all the companies that come in because then it's calibrated ground truth, right?
Okay.
All right.
I mean, in a way that makes sense. So now, but isn't it much better to look at, because you can see from space, you can actually see soil conditions, you can see the crop yields themselves. There's
How dry it is.
how
everything?
dry
Yeah,
you can see, there's so much more information you can get from looking down from above. So what's going on with that?
I mean, and so to your question, right, there is tons of NASA data that looks at the soil moisture, it looks at sort of the different vegetation, and that's all publicly available both to the agriculture department and anybody else.
And to the person pacing cornfields.
Right.
Correct.
It's available to them,
Right.
but maybe they need a job.
Exactly.
The farmer needs a job. I don't know. So I'm intrigued by this. So that was a tour of duty. It went across the administrations.
That's right.
But then you told me offline, you ended up at the Office of Science and Technology Policy,
Nice.
which is the executive branch that oversees the budget for science in the United States.
Wow.
For science, yeah.
For science, right. And so what were you doing there?
What are we doing with that $13.26?
What are you talking about?
You said the budget for science.
Oh, it's a little bigger than that.
I was going to say, that's what it
There's
seems.
a lot of science that they apply to the military. And so then you're talking big bucks.
Oh,
Okay, I'm just saying.
There you go.
Like Department of Energy comes under that department.
That's some
okay?
nuclear stuff right there.
There's some nuclear,
Yeah,
totally
some
nuclear
stuff.
Some nuclear stuff going down.
Right on.
Okay, so go.
No, I mean, writing about, hey, what are we investing in? What are the people and the programs? And I figured that we added the word American in front of everything we want to do. So we wanted American health, right? We wanted
Not just health.
American health.
That was smart.
Thank you. Yeah.
I mean, that is brilliant because
Oh.
when you look at Congress, America,
America.
you should have made it that instead of American.
You got to spell it right. Apostrophe M-U-R-I-C-A. America.
Merc.
They didn't teach me that one in my spelling classes,
Okay, so that was clever. And so now more people across the aisle can take ownership of it.
Right.
That's right.
Yeah.
Yeah. No, I mean, I will say, coming in to a new administration, it's kind of crazy. Your hard drives get wiped. Everything is gone. You're starting fresh a little bit. And lots of opportunity to learn. So whether you wanted me to have that opportunity or not. But I think, we did some good stuff.
But would you have normally been discarded between administrations?
No.
How did you stay on?
So White House Fellows have a 1-year appointment that's fixed. And so started August of 2016, went to
So
August of
that's built in.
2017.
Oh, you started at the end of the Obama administration.
did.
Oh, so you crossover.
You were a part of the transition.
I was,
Oh,
yeah.
Okay.
yeah.
Wow.
Very cool. So at the time, you told me again offline that you knew I was on a Pentagon board.
Yeah.
At the time, how did you know about that?
Because I go into 5-sided buildings. I can handle that, not just 4-sided ones.
Okay,
Right?
right on.
How many 5-sided buildings do you know?
I don't know because I work at the Hexagon. Okay,
I mean,
That's top secret.
that's
why do you think the telescopes have these hexagonal mirrors, right?
Yeah,
I mean,
yeah.
so I
The mirror segments of JWST are hexagonal.
That's right.
So that's top secret. Nobody knows about except for you.
There you go. That's right.
But
And
I'm-
you know where we came up with that idea? At the Hexagon. not the Pentagon.
Okay. What's your most recent published paper? Was it about climate change?
Yeah, we just wrote a paper together about sea level rise and how you can use satellite data to actually do better job of preparing coastal cities for sea
Excellent.
level rise. Yeah.
Where-
Which is
where-
only where like most everybody lives.
Every major city is
Yeah,
on a,
it's on a coast.
Is on a body of water.
Water, right?
And so
Lakes, rivers. What can satellites do for you, right?
okay, but again, it sounds like the seismologist. It's like, here's what to do when the water knocks at your door. is there preventative
No,
advice
so this
in
is
there?
all about how cities can look at, glaciers in Antarctica and, Greenland melting now to prepare for what's happening in
gonna
the
happen to
future,
them.
right?
Correct.
Rather than waiting for the level to actually rise, that you have some
then
early
react.
warning.
Oh, so you can make predictions.
Yeah,
and
exactly.
anticipate. Got it.
That's amazing.
Got it. And plus, I'm not thinking about Antarctica or Greenland
Exactly.
when I don't live near them.
Right.
But their water doesn't carry passports, right?
That's right.
That water molecule go wherever it goes.
Yes, exactly.
So let's get back to exoplanets.
Absolutely.
So your work for your PhD was what?
Thinking about how planets form and how they evolve over time.
Oh, formation of exoplanets. Good.
Nice.
So somebody had to make them.
That's right.
They're not just born whole.
No, exactly.
Okay.
Yeah.
So Chuck, you got questions for us?
We have them right
So
here.
let's do it.
You want to jump right into this?
Let's do it.
Let's
All
try.
right. I love this first one. This is Monshel Hicks. And Monshel says, "Hi, Dr. Tyson. Hi, Anjali. Planets are evaporating?" That's it. That's all that it says.
I mean, Montreal's got it down. Planets are evaporating,
Right.
right? I mean, we got the Earth, we got exoplanets, right? Because you've got all this gas that we call the atmosphere that's trying to stick to the planet by gravity, but sometimes you got the heat from that star that's enough that it just pulls it off.
Well,
and it
we're
goes
losing what? Helium and what's the other thing? that we-
hydrogen,
Hydrogen and helium on a daily basis.
hourly, minutes, seconds, yeah.
Wow.
Okay, but not so fast that I should worry about it and make a thing on. But if there's stars that get brighter or more luminous and they're gas-rich
Right.
planets, so how about those big Jupiters that are orbiting close to their host star? Are they evaporating?
Yeah, these planets, right, that we call hot Jupiters because they're so close in,
Right.
right? And especially since they've always got one side often facing the star, so the same side's
Because
getting
they're tidally
blasted.
locked.
Exactly.
Like the moon is tidally locked to us.
Right.
If you get close to a massive source of gravity, it's going to lock you
Right.
and only look at one side, just as we did to the moon. The moon is trying to do that to us. Did you know that?
Just lead us down the wrong path.
It's just
A
trying to-
new path. A new
Like
path.
a new path. Don't value judge the path.
A new
Yeah,
path.
it's just the orbital mechanics of it.
Come on, we going over here. Come on, why you?
I'm just saying.
Let's go over
So the
here.
moon is trying to slow us down, so
Right.
we only show the same face to it.
Yeah.
Yeah,
Right.
that's why we throw in leap seconds every now and then to make up
Right.
for that. But anyhow, so
So wait a minute. With the evaporation, just because I'm concerned about Earth, to be honest. What's going to happen first? Will our atmosphere, which I understand from Neil, is like thinner than the skin of an apple, okay? It's thinner than the skin of an apple. Will that evaporate before the sun expands and kills us all? Or what's going to happen first?
All right, Chuck. Don't worry about it. Don't worry about it. There's a lot of things that'll scare you with. This isn't one of them,
Okay.
right? So the idea is that you will have this atmospheric escape, is what they call it, because your atmosphere is literally escaping the planet, happening more and more in the future as the sun gets brighter. But it's not all going to go away before then. So you're safe.
Okay, so
You're good. But again,
we'll
if
be
you were
crawling around the surface of the Earth trying to breathe.
right, stay low,
Stay
like you're in a fire. Stop, drop, and roll, just so you can breathe.
well, I think you're gonna want to, go up towards the poles or something like that. The equator's not gonna look so hot,
Oh,
or maybe it is gonna look so hot.
yeah, that's the problem.
Okay. Well, you already got this planned out. You can move to join a Santa Claus. All right, what else you got, Chuck?
All right, here, this is TJ's show, who says, "Hi, TJ here from Winnipeg, Canada, eh?"
He does not have that in there.
No, they don't. Okay. They do not.
Okay.
Okay. It says, thanks for taking my question. Hello, Dr. Tyson, Dr. Tripathi, and Lord Nice, longtime listener, new Patreon here. My question is about intelligent life. If there are roughly 10 million unique organisms on Earth, 99% of all species that have ever existed are extinct, and we are only the only intelligent species out of all of that. Questionable. Let me say, questionable.
Big assumption. Yeah,
Big
go ahead.
assumption. Then doesn't that mean that the likelihood of there being intelligent life on a newly discovered habitable world is about 1 in a billion?
Oh, I like that.
Okay, so there
It's
you go.
fast back of the
Fa-
envelope math.
Back
there.
of the envelope math there.
Yeah.
So he says, yeah. So and then he goes on, our galaxy might be teeming with life, but intelligent life could be extremely rare.
So let me recast that in another way. So
Go
if you have so here's Earth. There's this one branch of vertebrates coming out of fish
Right.
that became great apes.
Right.
Okay. I know some apes, but not all of them were great.
Well, no,
So-
some of them were just not so great.
So, and one thin branch of that are the humans. Anything could have stopped that.
Right.
The asteroid not taking out the dinosaurs would have disrupted the mammals from ever even, quote, ascending to where we
where
are.
we
today.
are.
Just sheer luck.
Exactly.
Okay? Bad luck in dinosaurs. Good luck. So, if this is just one branch out of the tens of millions of life forms, if you have tens of millions of Earths, close your eyes and throw a dart. Really? Most of them will just have life like we got here.
Just life, but it
Just
will
life.
not be developed.
So react to that,
intelligent
please.
life.
I'm just saying I'm not smart enough to know what else is out there in the universe, and certainly not the numbers of that. So I think, if we're being honest, do we know if there's life out there? I don't know. Do I hope there's life out there? Heck yeah. Do I hope it's intelligent? Heck yeah. But the number's
let's
1
take-
in a billion?
Let's take the intelligence out.
Okay.
Now, the fact
It's already
is,
out.
let's factor that out. What is the likelihood of just life? I don't care if it's single-celled life. I don't care if it's just, some type of bacteria, amoebas, whatever. What is the likelihood of that happening, seeing as how, the same building blocks that we have here
Are
are
there.
everywhere?
Yeah, plus it happened pretty quickly on
And
Earth.
yeah,
Right.
yeah. I mean, we're only 4.5 billion years old, and we got to the life part pretty damn quickly.
I mean, there's planets everywhere, right? Like every star has planets. And so if you think about it, we've got so many planets, so many balls of rock are probably amongst those planets. Chances are good you had the conditions for life, right? And you had water, some energy. Those things seem like they're out there. So I think the chances are good. But again, 1 in a billion? I don't know if it's that slim.
Yeah, plus we're not even limited to rocky planets anymore because there's some good moons.
There are some great ones.
Right.
That habitable
Nice-looking moons.
worlds,
Yeah,
right?
yeah,
Not just the habitable
It's
planets.
habitable worlds, not just planets.
There you
Right.
go.
World. Forget planet, non-planet. Yeah,
Right.
have world.
World.
There you
Yeah,
go.
Okay.
And then yeah. I mean, like even like a ice. Well, what would be like an ice world, like Enceladus? So
Yeah, you got that water underneath, right?
Yeah,
Yeah,
but
yeah.
that could happen, right? Like, okay.
Totally happy.
All right, here we go. This is Dylan. And Dylan says, greetings, everyone from Flagstaff, Arizona.
Nice.
I'm taking undergraduate astrophysics courses and learning about spectroscopy. Thank you.
Spectroscopy.
Spectroscopy.
Yes,
I can't.
you
God,
got it.
that always gets me. And other amazing methods of how to find and characterize planets. What has been the best method so far to find planets, and what possible new methods are being thought up?
So let me focus that down and have you tell us. We're now using spectroscopy to study the atmospheres
yeah.
of these planets. So what's coming out of that?
I mean, it's amazing that when you get just the right configuration, that you've got the star and the planet passes in front of it, and you're looking at that, some of the light goes through that atmosphere
Right.
of that planet from the star and gets to us. And so we can actually see some of those chemicals in that atmosphere.
It's amazing.
So we see all
So the
carbon-
chemicals are disrupting really the clean path of light
Exactly.
from the star,
Amazing.
and that disruption shows up in the spectrum.
right? They were like putting their fingers on there, getting those
Get the
finger
fingerprints.
burns.
Yeah.
Right?
So what are you looking for?
So we've seen carbon dioxide with the James Webb Space Telescope, which is pretty
Okay,
cool,
that's
right? The
pretty
first
cool.
time we've seen that on another exoplanet.
All right.
Right? All kinds of other compounds, right? We get water,
Okay.
right?
Sure. Water molecule. Yeah.
Right? And you got some good things in there. And so all kinds of configurations of oxygen and carbon and hydrogen that you're
One of them.
Think about-
methane.
methane is
Yeah,
pretty
right.
great, right?
You get methane there too. Have
There's-
you seen it yet?
There is methane about on the planets, yeah.
Okay.
Okay.
Yeah.
That
All
would be evidence of.
Farts.
It can be. It can be.
All right. Keep going.
That
Check.
is so cool. This is Cesar.
Oh, by the way, just to bring closure to that, to say that the boring, obvious fact, so many of these planets were discovered
Exactly.
just by their spectra.
Right? And by transits, right? That you looked at the light and you saw it blinking, and that's just because
Looked at
something
the light
kept
of the
going
star.
around
Right.
at that light of the star.
And the transit is the planet going in front of the
Exactly.
star's light,
Right.
blocking the star's light.
It's just like when we have eclipses where you block out the whole face of the star, but here it's just a fraction of it, right?
That's
So we
amazing.
talk about
Yeah. In fact, solar eclipses are really transits.
Yes.
we talk about the transits of Mercury and Venus,
Yeah,
or
yeah,
little
yeah,
black
yeah.
dots.
Mercury transit, Venus transit, it's a moon transit.
That's right.
And an eclipse, technically, astronomically, is just object moving into the shadow of another object.
okay.
So a total solar eclipse, really, we shouldn't use the term eclipse, but we do.
All right.
Yeah. Thought I'd say
Nice. This is Cesar Erno, who says, hello, Dr. Tyson, Dr. Tripathi. Is the James Webb Space Telescope used to look for exoplanets?
Heck yeah.
Okay. So why don't we just zoom in on some
Wait,
exoplanets
see,
and
she
get high
works for
quality?
NASA. She said, heck yes.
Heck yeah.
Heck.
We heard
Heck.
that.
No, let me hear it real. You're in New York City. You're in Manhattan. Say that right.
Yeah. I'm sorry.
I don't think I can beat that. I think you
so
could.
sorry.
Chuck wins that.
I'm sorry.
Chuck did that.
That was just too New York. I couldn't help it.
That's a long bleep on that one. Okay.
No, I think if I had the teacher, instead of I love New York, it would be I love GWST, right, for the exoplanets.
Oh yeah.
James Webb Space
So
Telescope.
so I thought it would only be looking closer at exoplanets we've already discovered. Is there a discovery mode?
There are discoveries too, yeah.
How does it do that?
I mean, it actually captures pictures where you see that there's planets in the frame.
Wow.
Without knowing that in advance.
Yeah.
Oh.
So he said, why don't we just zoom in and get some high quality images?
That's what it's doing.
And that's exactly what you just said it's doing.
Wait. So you see the host star and you see the planet.
You get a hint of the planet being there.
A hint of the planet.
You get a little dip of tea, right? Dip of planets.
Gotcha.
But the question of can we zoom in on planets there? James Webb is looking at different patches of sky, and if there are planets in there, that's great. But it can't look at just any part of the sky and say zooming in deeper and deeper, because planets don't give off a lot of light. They're just reflecting their starlight, which is so faint that you don't see it most of the time.
Yeah.
Gotcha. All right, this is Gavin Bamber, who says, hello from North Vancouver, where plant life flourishes. And he's not lying. That's a
Northern Vancouver.
Ooh, it's so green up there.
Really?
Yeah.
Oh, you can go green blind up there. It's crazy. It's crazy. He says, once we find plant or animal life on other planets, will we be able to eat it? Or can we tell if we're able to eat it? Or for Chuck, will we be able to smoke it?
Well, that's a question for you, Chuck.
Wait,
did he say that?
Yes, he did.
No, he didn't.
Yeah, I swear to God. He
No,
said,
he
or
didn't.
for Chuck,
it says so.
will we be able to smoke it? But
Okay, so let me ask this. So can we only, I don't know how much biology you know, but can we process organic matter that has a different DNA from us? Like our DNA is right-handed, like it spirals this way.
Yep.
Like clockwise looking up.
a double helix.
But in principle, you can have DNA doing the other direction.
Right.
But the chemistry shouldn't matter.
Right.
All right. Except we don't.
And all those people's skin is on the inside of their body. That's how all their organs are on the outside. They are so messy looking.
So what is the scholarship on just the digestibility of life forms that are not native to Earth?
A researcher doesn't eat and tell, Neil.
A researcher doesn't eat and tell.
I don't know why that got me.
But I mean, I would say, would you want to though, right? Because I mean, there's so many things that you're like, oh, that cheese doesn't look quite right. I don't know if I want to eat that. Now you're going, I just found this out there. I foraged for some wildlife.
Yeah. That is funny because
tasty.
a whole lot of stuff on Earth you know not to eat. Now you that desperate to eat aliens?
Right, I'm just saying, would you want to?
So this is Daniel L. Thompson, who says, howdy, Dr. Tyson, Dr. Tripathi, and Sir Nice. That's Lord Nice. He says...
Lord is above Sir.
Lord, exactly.
Yeah, Lord is totally above
why
Sir.
would you demote me?
Mhm.
He goes, I'm Daniel from high school in the AF JR ROTC, a Junior Air Force Reserve Officer Training Corps. Good for you, buddy.
Nice.
He says, has there been a minimum and maximum size or density to define what would be survivable for humans
I like that.
to live?
I like that.
Yeah, and P.S. Chuck, you're welcome for the easy name. Well, thank you, Daniel. But you can't take credit. I'm gonna thank your parents for that. But anyway, is there? I mean, I suppose planet sizes and the pressure, atmospheric pressure, or gas planets, whatever. All those things would have a.
There was a movie, The Space Between Us, where someone grew up on Mars. An astronaut got pregnant on the night before the launch.
Yeah.
And it takes 9 months to get to Mars.
Right.
And NASA had to hide that information. So she gave birth on Mars and no one knew about it. And then the kid came back to Earth and it was like,
That's pretty cool.
he had a hard time breathing.
Yeah.
And all the things he was used to on
So on
Mars,
Mars,
his
he
muscles
can't-
couldn't
yeah,
handle.
can't-
But he was still alive. It didn't kill him. So do you have any thoughts on survivability of low or high gravity?
I mean, I'm a big fan of Earth, right? So like looking for planets like
Right.
Earth, because, I like being able to jump up and down rather than Jupiter. I don't know, jump up. Where are you going next, right? All right. And, having that nice solid surface. So, something sort of the size of Earth is nice and cozy. I mean, we seem to do okay.
Oh, wait, so your point is if it's much more massive than Earth, it's not a rocky planet. It's gaseous.
You're getting
Because
gases.
it kept all of its gas.
Right, yeah.
Okay, so that's out. The upper end of that's
Upper
out.
end's out.
Okay.
I don't know how low we can go, right? Because we've got moons
Mhm.
that are possibly good places to live, right?
Well, our moon is 1/6 gravity.
Right.
Right. So That's not going to kill you.
It's not going to kill you. You're going to get some
But
help.
you don't want to
right?
get used to it and
I
then
was
come
gonna
back to
say,
Earth.
yeah, I mean, 3 generations later, you have the bone density of a marshmallow.
But you've got the spacesuit, right? That, it's a souvenir, right? All I got was this lousy spacesuit, right? When I came. You're not going to be buying for my souvenir shop anytime
No.
soon, are you? All right, I understand. It's okay. So, I mean, I think, down on the lower end, it's hard to say how low you can go. It is interesting, though, that when we look out at exoplanets, we find some where there are these little planets that actually end up just getting evaporated away. So instead of their atmospheres being all that evaporates, you got just like crumbly planet going off into
wow.
space,
Wow.
right? So you got the wrong conditions there. So it's not just the size of the planet, it's how close it is to the star and
Right.
everything else it's feeling. So
It probably feels tidal forces that'll disrupt
If you
it
get the right-
structurally,
Right.
too.
yeah.
Okay,
so
but when they say super Earths, we've heard this.
that's right.
Yeah,
Bigger
among
than Earth.
exoplanets.
And nothing we
Super,
got.
how big is super?
Bigger than Earth, right? Smaller than Neptune, right? So you think like, that's in between.
So you might
Super.
be twice your
Twice.
gravity,
Right.
something like that.
Could
About
do,
10
right? We
times.
talk about it in terms of the radius of it.
Oh, right.
So how's the size of it? Because the super Earth, right? It could have a surface. It could be a little bit more puffy.
Okay, but so how big a radius compared to Earth if it's a super Earth?
Depends on your definition, right? It's a few times.
A few times, yeah.
Yeah.
Okay, a few times, but that's pretty
Okay.
big.
That's pretty
No,
big,
no,
right?
so
Like-
normally when people
Yeah.
think of, it's twice the size, but if you can range 10 and 100 times bigger,
Yeah,
a factor of 2 is just friendly.
yeah,
You know?
exactly.
I mean, we have a poster that we made of people skydiving on a super Earth because they thought, oh, that'd be fun, right?
Yeah.
You'd be falling faster.
I personally don't
A
think it would
lot
be
faster.
fun.
Yes.
But our art team thinks it's great.
Yeah,
and
no, okay.
I think that's great.
Yeah.
But, there was also the question in there of the density, right? And I definitely want to be on that ball of rock rather than that ball of gas like Jupiter
Definitely.
because I like having a surface.
Like you want to land somewhere. Okay.
Yeah.
And so, but what if, like, when we retrieved, part of the asteroid,
Mhm.
right? We were able to do so because we put the drill down in a place where we knew it was crumbly rock. So what if we know that it's a super Earth, but it's kind of made of that composition of crumbly rock?
I mean, I would love to get to that point, right? Right now, I'm just like, it weighs this much. It seems this big. Divide some numbers.
I don't
right?
think
Like,
that's a real thing.
Really?
Yeah, because if it's big enough and has a strong enough gravity,
Right.
it'll
It'll
compactify.
right. It
Right.
will condense.
The problem with the asteroids, they don't have much gravity.
Right.
Right.
So,
and that's
so
right.
they're like loosely,
Absolutely.
they're loose. Plus, it didn't drill. It was a touch and go.
It was right. It was bang,
It went
and then it
pshoo.
sucked up what was
grabbed
right.
whatever.
whatever
popped
came
up
up
in it.
inside of it. Yes.
Right. And they were ready for just a couple ounces.
Yeah.
They got half a pound.
Right.
Half
Right.
a pound. So they were good.
But no, you're right. The gravity makes that makes sense.
I mean, you
Thank
got to
you
be a
for telling me
planet, right?
Yeah.
Got to be a
I'd
planet.
live to have you say.
You try that. You try that. I was just like, you know what, Neil, you're right.
All right, we got time for like one and a half more questions. All right.
One more. All right. Okay, let's go with Andrew Nisker. And Andrew says, hello from Flesherton, Ontario. Can you please explain the different types of biomarker gases? How will the next generation of telescopes enhance our ability to study exoplanets? Guess that's 2 separate questions, but hey, I'm always looking up, so I have to ask lots of questions.
Nice. So picking up
All
on
right.
the earlier question,
Yeah.
you mentioned water molecule, methane,
Yeah.
and carbon dioxide.
Right.
But is there like the greatest hits of what would reveal life on the surface?
I mean, there's so many different ways that we can search for exoplanets with life, right? Those signatures, right? We call them biosignatures or technosignatures if you even want to go a little further afield. And so the fact that, you could look for pollution on a planet,
That'd
right?
be a technosignature.
Or depending on how you count it,
Okay,
yeah.
all right.
Right, but I mean, like you look for chlorofluorocarbons, right? From your, hairspray on your
Right.
alien world.
Okay.
That would be a slam dunk for life, even though it's not one of the things we've historically always studied, right?
Right.
These sorts of things. And so, signatures like methane,
Wait, so if the chlorofluorocarbons, they're idiots.
but they're idiots we can see, right?
No sign of intelligent life there.
Exactly.
They're getting rid of their ozone layer.
Which is probably what they're saying about us when they actually see the biomarkers from this planet, or the techno markers from this planet. They're like,
Right, I mean, it's like, if you were really smart, would you want people to see you and find you?
Right.
Whole
So,
separate
so anymore,
question.
what's the phosphate was one of them?
So phosphine is something that
phosphine.
people have talked about
Excuse me.
possibly, no, it's all good, it's all good. Being detected possibly in Venus, and whether that's a sign of life or something else, it's probably something else there. But I think there are lots of detections of all of these more complicated molecules, right, where you start putting things together.
That would be there only if you had life on the surface.
that could be caused by life, right?
Right, okay.
You know, like the chlorofluorocarbons would only be caused by
Okay,
life. But
and-
methane could be common from something else.
Something else.
Okay, because you can get naturally occurring
Occurring
methane.
methane.
Right,
Okay,
yeah.
so what about oxygen?
Oxygen could be there. It can be, I mean, when you look at,
I don't know how you get oxygen unless somebody's making it, like with plants.
I mean, like, look at the history of the Earth, right? For billions of years we've existed, and we didn't have this much
We didn't have
oxygen
oxygen,
all
right.
No,
that
that's
whole
what I'm saying.
time, right? Like,
Yeah.
go back in time. So you not only need to look at that planet and just see what it is, but at this particular moment
Right,
in
because
time.
when I saw the original Star Trek, do you remember that in the original Star Trek, no one ever wore a spacesuit
No,
when they went down on
they
the
didn't wear a
planet?
spacesuit. They never wore a mask
Right,
or
right.
anything.
You know why? Because they would establish oxygen, nitrogen, atmosphere, Captain.
Yep.
Well, let's go on down.
It's a Class M planet.
Right,
with
exactly.
breathable
So
atmosphere.
I'm thinking, oh, if you just look hard enough, you find other oxygen, nitrogen planets. And then I realized later that you're only getting the oxygen from living matter on the planet. It's not just some random mixture
Right.
in the random assortment of planets. Somebody's making the oxygen. And on Earth, it's our plant life.
Plant life.
But I mean, we can also, you know, when you form a planet, you got all kinds of chemistry going on in there and things going into the rocks. And so what goes on in your atmosphere, some of that just happens naturally.
Okay.
Okay.
So,
So you're going to have to distinguish those
that's right.
cases. And that's so getting the list is one thing, and then you fight about whether it's biological or not.
Exactly.
Yeah, at the
Yeah.
conferences. Yeah, that's good.
That was a good question.
Chuck, time for one half a question.
Oh my God. Let's see. Let's go with Captain James Riley, who says, hello, everyone. Texas here. Is there a most common atmospheric composition out there among rocky planets?
I like that. That's related to that last question.
Related to
I
the last
love that
question?
question. And I think in the last question, he asked about the telescopes. And I think the answer is we need more data, right, to answer this because we haven't been able to tell the
I'm
atmosphere.
not allowing you to cop out and just say we need more data.
No, no,
Talk to me.
No.
Give me.
But I mean, I think that's the thing is that so many of these things, because if it's a cloudy day, you can't see what's going on underneath, right? You see clouds, you see like water vapor up there, right? So there's so many of these systems where you think like, hey, I need this new telescope.
Okay, so of all the planets where we know anything about their atmosphere, is there an emergent common list?
I think it's
Yes.
kind of like the zoo, right? There's some common things, like there's all those things with tails, so there's all those things with oxygen, there's all those things with carbon and methane, right? It's the sort of thing that we haven't seen enough to be able to say this is the most common thing yet. So not yet.
So like the zoo, you have animals with tails, animals with 4 legs, and
Things with wings, right? Like it's just
okay,
you
so
can
there's
start
the blunt,
classifying
the
them.
blunt. You start blunt.
Right.
Start. I think what it means is we got to chat more again in a few years, and then we can do better.
Oh,
on
then
this
we should come
question.
back.
Come back.
Well, very cool.
Yeah.
By the way, I understand you have a TED Talk.
I do.
Yeah, on.
On atmospheric escape.
Well,
Oh, okay.
okay. Well, I'm not watching that.
I-
I'm scared to death.
but you know that how it ends.
Well,
you know you're
that's true. I
safe,
do
right? You know how it
ends.
ends.
I'll
so
die
no
long
problem.
before. Yeah, I'm
So
good.
you're the first to model the escape of gas from atmospheres.
Doing that in 3D for these planets.
3D modeling.
Yeah.
So
Oh, cool.
in the old days, computers weren't fast and we didn't
Yeah.
have AI. And so you do like 1D modeling and 2D modeling just to approximate the 3D
Mhm.
modeling because you couldn't calculate it. And then when computers get fast enough, then she comes along, says, I got this 3D,
Boom.
all in.
There you go.
And it's hard because you're modeling gas.
Right? You're just watching it flow.
Yeah. The flow of gas in a computer model, that's not easy.
It's not let it go, it's let it flow, right?
Right. Okay. But I mean, what's funny is like, isn't that like gas is, what's that? As it, gas moves towards entropy. It's just chaos, right? So what do you?
Somewhere in between, right? Because it was starting on the planet in the atmosphere and just blowing off into space.
Okay, so that's what you're doing. You're going from where it's
Pure
very more
coming out.
stable and then
Right,
to its instability.
There you go.
Okay.
Okay.
Yeah.
All right. We're good. Chuck is good till the next time.
I'm feeling better.
We feel a little
That's
better.
good. That's
I'm feeling
good.
better.
I mean, you got to be feeling totally better. Right?
So, Anjali, thanks for coming on to Star Talk.
Thanks for having me.
We'll continue to follow your career.
Appreciate that.
There's still a few more presidents you can
Yeah,
work for.
exactly.
Don't slouch.
Work on it.
You got to get back in the White House so that
Yeah.
we can. Yeah.
I mean, I'm the exoplanet ambassador though right now, right? So got to go visit those exoplanets too
You
eventually.
have an ambassador title.
Oh yeah, no, I'm NASA's exoplanet ambassador.
Oh, sweet.
Oh my God.
That's very cool.
So do you speak at the UN?
I speak for the State Department.
The Galactic UN.
Oh, yeah, there
That's
you
where
go.
You get to speak. That's
So when the aliens come, when
Right
they say
here.
take me to our leader, I'll say, well, we have an ambassador.
We have an ambassador. Is that good enough?
Yeah.
Something like that, yeah.
No, we say we ain't taking you to our leader.
Yeah.
You're the ambassador is going to be what you're going to meet.
But believe me, yes, it will. It will be a scientist or Taylor Swift.
The doctor will see you now.
All right. Well, good luck in your continued
so much.
career and your ambassadorship. And we'll want a full update
All right, sounds good.
as more exoplanets show up and more aliens visit.
Okay.
You'll be first on the list.
All right.
Nice.
All
Thanks.
right. Good. This has been Star Talk. Neil deGrasse Tyson here, your personal astrophysics. Chuck, thanks for
Always
for
a
being
pleasure.
there. All right. And as always, I bid you keep looking up.